So I'm going to present to you the work that we've done with Barrett and Tim Dwyer from Monash University, and Antoine Lhuillier and Daniel Weiskopf from University of Stuttgart about the routing of visual links in immersive environments. So first, what is a visual links? So a visual links is a line between two visual elements in a visualization that is here to visually represent the relationship between these two elements. They have been extensively used into the interface. So, for example, in Connected Shark by View and McGuffin, they've used visual links to link visual elements that belong to the same data points. In this work by Wallner and colleagues, they've used visual links to link elements in different windows in the user interface. So elements that are connected, that talk about the same thing. Visual links have also been used in immersive visualization. For example, in this work by Hens and Irani, they've used visual links to connect elements in to connect elements in different windows in a spatial graphical user interface. And in this work by Serrano and colleagues, they've used visual links in an augmented reality interface to link physical devices that are connected between each other. So visual links is a very efficient way to make this relationship explicit. So as you can see in this example, it's very clear which elements are lit between each others, but it can get a bit more cluttered if you have a lot of them at the same time. So it gets cluttered, it's hard to follow one links, and it actually can cover important contents. So researchers asked this question, how to use the routings of the links to actually avoid clutter and improve the readability of the links. So in this work by Steinberger and colleagues, they've used an optimization algorithm to actually improve the readability of the link and avoid having the link cluttered the visualization. And in our paper, we take inspiration from this method and apply it in immersive environment. So our requirements are to avoid clutter, but also to allow the following of individual links, or on the contrary, to highlight general pattern in the structure of the visual links. And so because we are in immersive environment, we want a link to avoid occluded physical or virtual objects. So to this purpose, I'm going to first present a design space for the routing of the visual link in immersive environment. Then I'm going to present a four-space model that allows for real-time interactive link routing, and that allows to do most of the combination of our design space. And finally, I'm going to present a few use cases of this fourth model. So let's have a look at the design space first. So we have 6 dimensions in our design space. We have a link-link visual separation, link-object visual separation, link-link angular resolution, link-object angular resolution, view dependence, and MultiView coordination. So the first one, link-link visual separation, is basically if you want the link to repulse themselves, meaning that it's going to be easier to follow one link. Or on the contrary, you want the link to attract each other. And in that case, you're going to create bundles. And so it's going to be easier for you to see the main structure of the links, of the link visualization. Similarly, you can have the same concept between object and links. Maybe you want your link to actually avoid virtual or physical object in your scene, or you may want to use object to actually constrain the trajectory of your links, and so you're going to have the object attract your links. The angular resolution, so it's basically how links cross. So do you want a clean perpendicular crossing between your links? In that case, it's going to be easier to follow one link again, or you may want parallel crossing. So in this condition, again, you're going to improve the highlight of the general structure of the links. And similarly with object, maybe you want your link to cross perpendicularly object, so for example, to improve readability. Or you may want to use a plane, for example, the surface of a plane to actually constrain the trajectory of the links, and so have them just follow this surface. The view dependence is really the first dimension that is really specific to immersive environment. So because you are in an immersive environment, your perspective of the visual links routing is going to change with your position. So if, for example, you have one good links routing, if you move a bit, maybe it's not going to be as good as before. So to solve that, we actually propose to have a link routing that is dependent on the position of the user. It means that the calculation of the position of the link is going to be done in a local local coordinate system centered on the user. And if the users move, the link routing is going to change interactively. On the other hand, maybe you want a link routing that is completely independent of the position of your user. In that case, you just calculate it in the world coordinate. And finally, the last dimension is the MultiView Coordination. So if you have several users looking at the same visualization, and that if you use a view-dependent algorithm, in that case, maybe you want to show them, each of them, the best link routing for their own position. In that case, their link routing will be non-coordinate. They won't see the same link. But this can actually get problematic if they want to closely collaborate, if they want to discuss about this visual linking, because they won't have the same one. So in that case, maybe you actually want to choose a solution which is suboptimal, but is coordinated between the different users. So as a very quick summary, our design space is composed by 6 dimensions, so link visualization and link object visual separation, link and link object angular resolution, view dependence, and multi-view coordination, and it really acts on the trajectory of the link. It allows to really have several combinations of the trajectory. This is not the only way of actually improve the readability of visual links. You could also directly play with the visual attributes, like the colors, like the transparency, and this has been actually studied by Buschel and colleague. And so we won't use that in our paper. Then we're going to talk a bit about the force-based model. So the force-based model is inspired by a work by Olten and Van Wyk, and this is just a very basic representation. There is a bit more complexity that is presented in the paper, and so if you want to have more information, I invite you to have a look at it. But so basically, we discretize our link in a specific set of points, and we apply different forces on the point. So there is internal forces that give us a spring effect that will give flexibility for the trajectory of the link, but we'll still try to keep it as short as possible. And there will be forces between the different points of the links and forces between object and the point of the link. And these forces can either be repulsive or attractive. So this is a short video that will show you a very, very basic example of our force model. And so as you can see, so the points are amplified in this video just to show you, to make it more obvious. And so as you can see, the point can attract or repulse themselves, and you can play also with object and repulse the point, and so move the links with them. One challenge in the implementation of this model was to the view dependency. So how do you calculate this force for the position of the users? So our first method was to actually use perspective projection to project all the points in the local referential of the users, and then calculate the force in this coordinate system. This led to a very unstable solution, which means that each time the user just rotate the head a bit, the link were completely going crazy, which was not really comfortable. So our third trial was to use actually a spherical projection to project the links, the points on the surface of a sphere centered on the users, and then to do the calculation on the surface of the sphere. This means that all the calculation is rotation invariant, so it's quite stable, and it was more comfortable. So this is a short video showing you how the link moves when the user moves his head. So it's As you can see, the movement are quite subtle, so it leads to a better comfort for the user, basically. Finally, a second challenge was how to coordinate this optimization across several users. So our solution is to first calculate all the forces for each users, and then to take the average position for each point. Of course, this leads to a suboptimal solution, so the solution is not optimized for any users. And our future work, in our future work, we will try to investigate a bit more how we could do that to have a better optimized solution. Now I will talk about a few use cases to demonstrate the use of this force model. So in this first use case, we will have Alice, who is interested in data on life expectancy and on GDP. And so while viewing a world map in the center, she links the data values of some countries to their geographical location. And so she can select several points by brushing with the controller, which will link the point to the map. However, you can see the straight links are kind of hard to follow. So she will increase the visual separation of the links. And now the layout is actually optimized for her view. And so as she moves, the link will move dynamically. So when too many links are selected, the space can become visually cluttered. So she can select and bundle some links together. So it will just increase the link-to-link attraction for this specific set of links. And when she wants to explore a specific bundle, she can just explode them. So just change the link-to-link attraction. So if she wants to explore the population of each country, she can add another graph, which is going to be linked to the map also. And finally, when she wants to present her findings, she will replace the 2D map with a 3D globes. And in order to make sure that no links will cross the sphere, she increased the visual separation between the links and the sphere. In this second use case, we'll talk about multi-user context. So we have Bob and Arthur, who are viewing a small multiples of temperature data in a building model. So they use visual links to actually associate each time series on the screen to the corresponding room in the 3D model of the buildings. So at the start of their exploration, Bob and Arthur have different links routing because they are really just exploring the visualization on their own. And so the link routing is optimized for their individual view. But when they are ready to discuss any findings, they will switch to a coordinated view so that they can both see the same routing layout. So in that case, as I said before, the route optimization is just a compromise between both views. But as you can see, we also make sure that the link avoid crossing the face of their collaborator. Finally, in this last example, where we're going to show a small use case in augmented reality. So Nathalie is looking at aircraft trajectory in an airport, and to view the flight destination as a function of their takeoff trajectory, Nathalie links them to a map on the computer screen. Okay. So to make the link follow the direction of the trajectory, she applies a parallel angular resolution. And to avoid the map, the link going through the maps, she used a repulsive spatial separation between the link and the map underneath. And she can also make the links avoid important real-world objects like a coffee cup by adding a repulsive forces. So at the conclusion in this paper, we presented a design space for the routing of link in immersive environments. We also propose a flexible force model that allows for a real-time dynamic link routing, and we demonstrate its use in different use cases. As future work, of course, it would be interesting to first evaluate this design space and this force model with real users to see which combination of the design space can be comfortable for user, useful, and which one can be a bit less uncomfortable. We also would like to improve the scalability of our approach. So for now, we handle quite well around 100 links. But if you go further, it's going to get a bit laggy, and so it was going to impact the comfort of the user. And finally, we would like to see how we can include more dynamic objects in this link model, especially in augmented reality. So thanks a lot for your attention, and if you have any questions, I'd be happy to answer them.
Questions?
Thank you for your presentation. Thank you. Francisco Ortega, Colorado State University.
All right.
I wanted to ask you, and I'm not trying to change any of the research you're doing here, but just your take on this. There's a lot of 2D visualization on this 3D space.
Yeah.
And I was wondering why. I mean, there may be cases that it's needed. I understand that, but why not exploit the entire the rich 3D space you have around you? And so I just wanted to get your take on this.
Yeah.
Right? It's not a critique on your work or anything like that. And I can say because we're not in InfoVis, they don't like the 3D stuff.
No, so I mean that's actually a very good question. And well, let's say, why didn't we explore a bit more the 3D visualization? It will actually work kind of the same. We would just use 2D visualization because we had a bit easier use case. So it was a really easy way to kind of demonstrate simply how to use these visual links. As soon as you had 3D, it became a bit more complex. So we had actually 3D in the last use case. So we had the 3D visualization of trajectory in that case. And we also in the first use case, we had the 3D globe. But that's true, I'd say, in the use case that we demonstrate, it's more 2D probably for more simplicity and not add more complexity to our use case and really focus on the visual links. But after adding 3D, it's completely possible, and there is nothing in our model that restricts that.
Other questions?
Lauren Thévin from LMU Munich. My question was, I have the impression that the repulsion between the links is in 3D, but I'm not sure if it's taken in account in the 2D projection. So can we avoid to see many crossings between the links when we see it from the perspective of the user? Or I don't know if it's clear.
So if I understand correctly, yeah, so the repulsion of the links is actually up to you, is how you want to do it in our force model. You can either do it in 3D, but we will still project, we will still do it on the sphere, so on the surface on the sphere, so it's still 2D, but it's not it's not regular 2D, I would say. And in that case, it's actually, you try to avoid crossing in this plane, basically, in this surface. You can also do it in 3D, and it's also possible to do it with our force model. But in that case, link cannot cross in the 3D world, but can cross. You can see crossing. So that's why we really focused, as you mentioned, on this point of view of the user and on this 2D space, on this 2D surface, on the sphere around the user.
Okay, thank you very much. Let's thank Arnaud again. So the last talk of the session